we're going to continue our discussion of control volume laws by looking at momentum. We're going to start with linear momentum, and we're going to move on to angular momentum. So we actually are going to start with the Reynolds transport theorem again. Now, again, we're going to decide what we need here. So we want momentum. Momentum is mass times velocity. So we need psi to be velocity. And if psi is velocity, then we can look at d velocity d time, which is acceleration, and we can see Newton's second law. So Newton's second law is force equals mass times acceleration. And the forces can be broken up into two different cases. Body forces, which are those that act throughout a fluid, like gravity, or surface stresses, like friction and pressure. For now, we're going to just ignore friction, but we are going to account for pressure. We're just going to call it surface forces. So from Newton's second law, we get sum of the forces is equal to the left-hand side of the Reynolds transport theorem for velocity. And we can break that up into body forces and surface forces. So then if we substitute this in with the Reynolds transport theorem, we can come up with our linear momentum equation, where the sum of the forces is equal to the local acceleration of the fluid plus the acceleration due to the flowing, moving in and out of the control volume. So the first two terms are our forces. The first term on the right-hand side is our local time rate of change. And then that third term represents the difference in the momentum of the fluid from when it enters the control volume to when it leaves the control volume. Again, be careful of the sign of the dot product in the surface integral. So moving on, we can expand this out. This is valid for an inertial frame of reference, which means it's not accelerating. So there's no acceleration of our control volume for this case. And it actually represents three equations, one in the x, one in the y, and one in the z. So here we have a body force, a pressure force, a friction force, and then what we call a structural force or an other force that's acting on the fluid. Most of the time for this control volume unit, we're going to ignore the viscous forces, the friction forces. So then we just have body forces, pressure forces, and other forces. And then we have one in the x direction, one in the y direction, one in the z direction. We can also apply the linear momentum equation to accelerating frames of reference, but we need to add an acceleration term to the equation. Now, when we start analyzing these systems, we have to be very careful to avoid mistakes in our signs or in the direction of our forces. So we want to make sure we draw the control volume, indicate our frame of reference, our x, y, and z coordinates, list out all of our important assumptions, draw the free body diagram, show the directions of all the forces, make sure you get the signs on all the forces correctly, and then write down the entire linear momentum equation, and then apply the assumptions and simplifications afterwards. So you start with the fundamental basic equation. Now, as with conservation of mass, we can simplify the linear momentum equation, right? We can look at steady state cases where we can eliminate the time derivative. That makes this equation much easier to solve. We can also look at incompressible flow, so we can remove the density from the integrals and the derivatives. If we can assume the flow is uniform, we can convert that surface integral into a sum over all the different areas, all the different inlets and outlets. Here we have to be careful again of the sign of the dot product, but we've already talked about that. And so we can actually reduce this to the sum of mass flow rates times velocity. So that allows us to further simplify. If we know the mass flow rate and we know the velocity, we can get the momentum in and the momentum out. Last, if we add all these things together, we can come up with a little bit of a simplified linear momentum equation. Here we have the change in the momentum of the control volume, and here we have the momentum in and the momentum out of the control volume, and then here we have the forces acting on the fluid. We also have an angular momentum equation which describes the rotation of an object, and it depends on torques rather than forces. So the angular momentum equation is basically r cross the linear momentum equation. So now we have to know where forces are acting and where the velocity is in order to compute all the values for this. It has applications. We can look at Euler's turbo machine equation. We can look at pumps, compressors, and turbines and things like that. But we're not going to worry too much about angular momentum in this course. There are important applications, and we'll discuss some of them towards the end of the class, but for now we're just going to focus on applying the linear momentum equation for solving problems.